Corresponding to a matrix, there's a function. If the matrix is an R by C matrix, then the function maps f to the c for some field f to f to the r. And the function is the function defined by the rule f applied to a vector y is a times y. Now let's consider two matrices A and B that we're going to multiply together. These define functions as well. A defines the same function, f of y is a times y. B defines a function, we'll call it g. G applied to a vector x is b times the vector x. And we'll define h of x to be the function corresponding to the matrix product a times b. That is, h is the function that takes a vector x to a times b times x. Now there's something interesting about the relationship between these functions. F composed with g equals h. Here's an example. Let's start with this matrix. The corresponding function multiplies a vector by the matrix, and this has the effect of adding the second element to the first element. Let's take B to be this matrix. Here's the corresponding function. It multiplies a vector by the matrix. And this has the effect of adding the first element to the second element. Now let's take the product of these two matrices. Here's the product. This corresponds to a function as well. Multiplies this vector by this matrix. And the result is here. Now, if we take the composition of the two functions, f and g, and apply that to a vector, looks like this. We apply g first to the vector x1, x2, getting x1 and x1 plus x2. Then we apply f to the result. We get the vector 2x1 plus x2 and x1 plus x2. And this exactly matches the output of the function h on input x1, x2. So this illustrates this idea that the composition of functions corresponds to multiplication of matrices. Let's see a formal proof, however. For the proof, let the columns of B be the vectors b1 through bn. Now, by the matrix vector definition of matrix-matrix multiplication, column J of the matrix product AB is A times column J of the matrix B. So let's take a vector x. Let's say its entries are x1 through xn. Applying the function g to x is the same as multiplying x by b. By the linear combinations definition of matrix vector multiplication, we can write this vector as the linear combination of the columns of B, where the coefficients are given by the entries of x. Now let's apply f to g of x. F of g of x is f of this linear combination. Using the properties of linear functions, we can replace this by this. We basically move the function in, move the coefficients and the sums out. And now, using the definition of f, we can replace f of b1 by a times b1, f of bn by a times bn. And now using the matrix vector definition of matrix-matrix multiplication, column 1 of AB is a times column 1 of B, which is a times b1. Similarly, column n of the product AB is the same as a times column n of B, which is bn. Now, using the linear combinations definition of matrix vector multiplication, the linear combination of these columns can be written as a matrix vector product. The matrix AB times the vector x, whose entries are the coefficients. And this, by definition, is the result of applying h to the vector x. So that proves the property. So we've seen that matrix-matrix multiplication corresponds to composition of functions. And this gives us a nice corollary. Matrix-matrix multiplication is associative. What that means is, in taking the product of three matrices, A, B, and C, you can first take the product of the first two and then multiply by the third, or you can take the product of the second and third and then multiply by the first. You get the same result. The proof is very simple. Function composition is associative, therefore matrix-matrix multiplication is associative. Here's an example. Three matrices. Let's say first we take the product of the second and third, getting this one. Then we take the product with the first, and we end up with this matrix. We could also first take the product of the first and the second, getting this matrix, and then multiply that by the third, and we get the same matrix.